chapter 10 test, even though on your, that's so weird. It is chapter 10 in your book. On your email, I said chapter 11. So I apologize if you're all confused with what's going on, but it is chapter 10. So let's do some review and talk about what we did before spring break and make sure everybody's ready for the test. So I have some kind of questions that some I might kind of make up on the fly, but I think you guys should be able to figure these out. So the first thing that I want to review is the idea of the fundamental counting principle. So this is the idea that you have different choices that don't depend on each other. For example, if you were picking out your clothes in the morning, this does not take into account what matches or not, but if you were picking out your clothes, picking out outfit, right? Okay, so let's say that you had 6 different shirts. You have 6 different shirts. You have 4 pairs of jeans, and you have 2 pairs of shoes. Okay, so the question is, how many possible outfits are there? Again, this does not take into account any type of matching. I mean, you have jeans, so as long as your shoes aren't, some crazy color, we're going to assume that they all match. So the idea of the fundamental counting principle, who remembers this, is that you take the number of choices that you have for the first and multiply it by the number of choices for the second and the third and so on. And you can just kind of infinitely go on with that. So what we're talking about when we're talking about picking out the outfit, we're not talking about probability, how likely it is that you'll pick this outfit, anything. We're just talking about the number of possibilities. So how many possible outcomes can we have? So who remembers, how do we solve this kind of problem? Are you guys still here? Yeah, exactly, Olivia. You got to multiply them all together, right? Easy one. So you have 6 possible shirts times 4 possible jeans times 2 possible shoes, which ends up being 12, 24, 48. Right? So you have, oh yeah, 6 times 8, 48. So you have 48 possible outfits. Right? So this is, again, called the fundamental counting principle that we do that. Okay. Another way that we thought about this, just to kind of go back and remember, is that if you kind of want to remember, you have your shirts. So you have your shirts over here. You have shirt 1, 2, 3, 4, 5, and 6. Shirt number 1 could have all 4 different pairs of jeans, and then each pair of jeans could have 2 different shoes. So this would probably not be a great one to make a branch diagram for. So this is your shirts, this is your jeans, and this is your shoes, right? But you could make a branching out diagram, and then each one of these shirts would branch out like that as well. So just another way to think about that fundamental counting principle. Okay. Everybody kind of remember that? I'm going to say yes, unless I hear anything differently. All right. You have, let's see. I'm trying to think of a way to ask this question. Let's see. Between my 2 math classes at Learning Tree, I have 6 and 5. I have 11 students. Okay. So I have 11 students in math at Learning Tree in upper level high school math. Let's call it high school math. Okay. And I need to get an opinion about, I have two, let's see, I have 2 committees that I'm going to make. So the first committee that I'm going to make is that I need a panel of 4 students from high school math to talk to younger students about how awesome it is and how awesome of a speller I am. No. Okay. So I need a panel, and that says panel of 4 students. That should say a panel of 4 students to talk to the younger kids at Learning Tree about how amazingly awesome Learning Tree is and how they should take math. They should go all the way through and take all the maths, right? So, of my 11 students, how many different ways can I pick a panel of 4 students? Is the question. How many different ways can I pick a panel of 4 students? So we're kind of mixing it up a little bit. Okay. How many different ways can I pick a panel of 4 students? So this is where we have to remember that we have something called permutations and we have something called combinations, right? So just to kind of review, we talked about these principles when we're trying to find the number of possibilities by choosing out of a group, right? So we have a group of 11. In this problem, we have a group of 11, and we need to choose 4 of them. So there's 2 different ways that we can think about the number of combinations when we're choosing a set out of a bigger group. One is called permutations, and one is called combinations. Okay, we'll start with the combinations because combinations is a little easier. Combinations tells you that the order is not important. So if I have my 11 math students and I pick 4 of the students out, it doesn't matter if I first pick Anton and then pick Noah, or if I first pick Noah and then pick Anton. There's no difference in that choice because I'm just interested in having a group of 4 students. I'm not necessarily interested in the order in which they are picked. That makes sense? So when you're not picky about the order, we call that a combination of people or combination of choices, I guess, not people necessarily. All right. So remember, a combination is when we, the order is not important. Okay. And a permutation is the one that I said, remember permutation by picky. So a permutation is when the order does matter. Okay. And these each have a formula that are slightly different. So the formula for combinations is, we call it the NCR, right? So the number choose R. And that formula is n factorial over r factorial n minus r factorial. Okay. The formula for permutations is a little bit different, and that is the NPR. Okay. And the NPR is n factorial over n minus r factorial. So one thing to think about is which do you think has more possibilities? Do you think that that when you are picky about the order, there's more choices, or when you are any combination, there's more choices? So if I said I wanted a panel of 4 students, or I want a panel of the first person I pick out of my group of 10 wins first prize, the second person, which one do you think there's more combinations for? So Aaliyah says not picky. It seems like, I agree, Aaliyah, it seems like that's what it would be, but it's actually the picky one has more combinations because, and that's what it's always a little tricky in my mind, because when I have the picky one, the permutation one, when I pick Noah first and then I pick Anton second, that's different than picking Anton first and Noah second. Those count as 2 separate choices. So the permutations usually is a higher number, a higher number. It's a crazy arrow, a higher number of things. Okay. All right. So let's get back to this problem. I have 11 students in high school math. I need a panel of 4 students. So I'm not picky about the order. So what I'm going to do is I'm going to do the NCR. So I have 11 students and I'm going to choose 4. So then you have a choice for this. You can actually mathematically do it, or you can use on your graphing tool, there is a button that allows you to do this. So probably what's crashing my thing. Let's see. Desmos. So I would go in here. Nope, I would not go in there. I would go down here, functions. It's under statistics, and it's the NCR. So here it's a little different. You have 11, choose 4. So there's 330 possibilities of my panel of students. 330 possibilities. Okay. Now, what if I was giving out a math prize, a random math prize, okay, and I had a first, second, and third place prize out of my 11 students? So I'm picking somebody out for first, somebody out for second, and somebody out for third of my 11 students in high school math. So what would that be? Would that be a combination of 3 students to win that prize, or would that be a permutation? Actually, I'm going to do a 4th place prize too. Yep, first, second, third, and fourth. Right? This would be an example of a permutation because whether Olivia gets picked first or Aaliyah gets picked first, if it's Olivia first and Aaliyah second, or Aaliyah first and Olivia second, those are 2 different possibilities, right? So then I'm going to use 11 pick 4. That's what I think in my head, 11 pick 4, right? And so I'm going to use either this formula again or use my graphing tool to help me do this. So instead of, well, let's see if it lets me do this. Well, it does. All right. 11 pick 4, and I have 7,920 ways that my math students could get first, second, third, and fourth prize. 7,920 ways. Okay. Total side note, if you have not updated Desmos, they did something that has bugged me forever. Whenever I would get a giant number, it's hard to tell like what place everything is, and they started putting the little space in between like each of the, the thousands, millionths, all that kind of thing. So just a little side note there. Okay, everybody, now that I kind of review that, do you remember talking about the picky, not picky kind of thing? Or you remember now that you see it again? Cool. All right. Side note in here, we didn't quite talk about this specifically. This idea of this N with the exclamation point or N minus R exclamation point. Anybody remember what the exclamation point stands for? It's a factorial, right? It's a factorial. And we can even more basic than this is that we could say, let's say, I don't know. Let's say you have eight of your favorite knickknacks. I don't know. You have 8 favorite things that you've collected and you want to stick them on a shelf. All right. You're going to put all 8 things on your shelf. How many different ways could you arrange those 8 things? So like you have, I don't know, an award and you have a book and a picture and whatever. You have 8 little things that you want to put on a shelf. How many different ways can you arrange those 8 things? So if you completely forgot, right, the order does matter. So if you completely forgot, really you could do 8, pick 8 things, right? Because that's what you're doing. You're picking the order of your 8 things. But we really don't do that. What you just need to remember is that if you have 8 things or 10 things and you want to put them in an order and you want to know how many possible ways that there are, we just can say that that would be 8 factorial. So the number of permutations of an object when repetition is not allowed, so we don't repeat our objects, is just 8 factorial, which does happen to be the same as 8 pick 8. They're the same thing mathematically, but just a simpler way is that you could just do 8 factorial. Okay. Any questions about that? All right. That's a beautiful picture right there. All right. Next, let's switch a little bit. So that was the beginning of the chapter where we were talking about the number of possible choices, like how many possible ways can we arrange 8 knickknacks, or how many ways can I pick 4 students out of 11? How many, some of their other problems were like, how many ways can you arrange the letters in Cincinnati? You remember doing that? So that's one choice, one part of our chapter. The other part of our chapter was that we started talking about probability. So the idea of probability is that you're looking at what are your total number of outcomes in the denominator, and you're looking at the total number of favorable outcomes in the numerator. Okay. So for example, what we use a lot with this is cards, right? So a standard deck of 52 cards. Right? What is the probability of picking let's see, what's the probability of picking a jack or a 3? Well, actually, let's just do what is the probability of picking a jack first. So there's 4 jacks in a deck. right? That's the number of favorable outcomes. And there's 52 cards, and you guys are experts at this. So there's a 1 in 13 shot at picking a jack, right? So we call that just general probability, right? What if we have two things? So if we want to know, we're picking one card, what is the probability that we would pick a jack or a queen? What is the probability we would pick a jack or a queen? Well, the probability we would pick a jack is still 4 out of 52, right? But it could also be a queen. The probability that we would pick a queen is also 4 out of 52. So the probability we would pick a jack or a queen is 8 out of 52, right? Or otherwise known as 2 out of 13. Okay. Everybody remember that? It's in there somewhere. I'm going to assume yes. All right. So then the question is, what is the probability that you would pick a jack or a heart from your deck? Okay. So this is where you got to think a little bit, right? The probability of picking a jack, still 4 out of 52. All right. What is the probability you would pick a heart? Well, a heart is one suit of the deck. So there's one suit out of 4. So there's 13 out of 52 cards are hearts, right? So you might think, all right, I'm good. I just add those together and the probability is 17 out of 52. The problem is that one of those cards you've counted twice. In here, you counted the jack of hearts. And in this number, you also counted the jack of hearts. So we've counted the jack of hearts twice because it's a jack and it's a heart. It belongs in both groups. So when we do something like that, we have to subtract out our double count. So we've counted the jack of hearts twice. So we need to take away one of those possibilities for the jack of hearts. Okay. So this is called when we have compound events. This event up here is mutually exclusive. Mutually exclusive. Okay. This event right here is inclusive. Mutually inclusive. Okay. So this event has something that overlaps between the two. So then when we do our math here, keep all our denominators the same, right? 52, 16 out of 52. You guys remember that? All right, cool. All right, let's do another one. So let's talk cards again. Okay. So this is when you're picking one card. What I was talking about here is you're picking one card of the 52. So what happens if you are picking 2 cards. Okay. So what is the probability of independent and dependent events? All right, so you guys were all pretty good at this, I remember. So again, we're going to do our cards. We have 52 cards. Cards are just great for probability. 52 cards. Okay. So what is the, let's see. Let's say, what is the probability? You're going to pick 2 cards. Okay. What is the probability that you pick a heart and then you pick a 10? Okay. Well, if you're doing that, what is the probability you pick a heart first and then you pick a 10? It's probably a pretty lowish probability, but let's figure that out. The question you should be asking is, well, are you going to replace the first card? Replace? I cannot write on the screen today. Replace the first card or not? Are you going to replace the first card or not? Okay, so let's say yes, we're going to put it back in. All right, so you have your 52 cards. What is the probability that you're going to pick a heart? That's a crazy heart. Probability you're going to pick a heart. Poor heart. There we go. Probability you'll pick a heart, everybody should remember, is 13 out of 52, right? What is the probability that you're going to pick a 10 on the second draw? Well, all the cards are back in. You replaced it back in. So there's 52 cards and there's 4 10s, right? So the probability you'll pick a heart and then a 10 afterwards, how we calculate that is we multiply these together. We call those independent events and we multiply them together. And so whatever 13 times 4 is, which is 452. 52 over 52 squared, or 1 out of 52. A pretty low possibility that you're going to pick that, right? It's still a possibility, but pretty low. Okay. What if we decide we're going to pick a heart and a 10, but we're not going to replace the first card? So we're not going to replace the first card. What does that look like? Well, the probability that we're going to pick a heart on the first one is 13 out of 52, right? The second card, our probability of picking a 10 is a little bit different because we have not replaced our first card that we picked. So we're going to assume we got a heart on the first card. So the probability of picking a 10 is 51, 4 out of 51, because we have one less choice. Right? And this isn't a great choice because there's some overlap, and so should we take it out? We should take it out. So there's the overlap that we're not taking into account for here. But let's say instead of a 10, we did like a, well, anything's going to overlap. That's a number card. Anyway, do you remember this idea that once you don't replace it, that we have to decrease the number of possibilities there? Okay. Let me look at anything else on the test that I want to go over. You guys all remember how we talked about Chipotle and Duck Donuts and the number of choices? So just kind of keep that in the back of your mind. Is there anything else in probability you guys want to go over? All right. I think you guys should be prepared for your test. I hope so. So I would encourage you guys to take it really soon. And on Monday, we're going to start chapter 11, which is, I kind of like this chapter. I think it's interesting. It talks a lot about standard deviation and sample size, and we talk about like bell curves and that kind of thing. So I think it's an interesting chapter, something kind of totally different. So I will see you guys on Monday. Thanks, guys. Bye.